Yeah, thank you. I will talk to you about a scalable approach for high fidelity simulation of wind turbines with the LBM. And my motivation is that currently in wind turbine simulation, they usually use simplified representation of the wind turbine. They often simplify the rotor either as a disk or when they want to have something more accurate as actuator lines, which is pretty similar to the inverse boundary method. There are some tries on more sophisticated schemes, but it's not like the usual. And these models are only suitable for far-away analysis. And since my aim is to work with the loads on the wind turbine directly, I want to have a full turbine geometry and want to do high fidelity simulations. And then I can hope to quantify the impact of the wind patterns on the turbine. Since I'm the first one in this lattice-Boltzmann session, I brought some facts for you. The lattice-Boltzmann method is based on the Boltzmann transport equation, which is like comes from kinetics. So it works with statistics, and we have a distribution function which depends on space-time and velocity. And for my scheme, it's important to see that we get the usual macroscopic quantities as moments, like statistical moments of the distribution function. I will use density, velocity, and velocity gradients. And for the velocity and the velocity gradient, we can use the central moments, or in this case, we call them cumulants, which are like independent moments, and up to the third moment, they're identical to the central moments, at least for 1 and 2. And we discretize the lattice-Boltzmann equation, or the Boltzmann equation, so it becomes the lattice-Boltzmann equation in space and time. And I will use for discretization the D3Q27 model. So we use 27 velocities in 3 dimensions. So the particles can move in all these directions. Yeah. The basic algorithm of lattice-Boltzmann has 2 steps. It's collision, which is local. So we only need the information on this stencil to do a collision. And the streaming, which is linear. So it's quite easy to do, but it's non-local. Just to show you, for you lattice-Boltzmann guy, which methods I use the cumulant lattice-Boltzmann method, which worked on these mentioned cumulants. So to do it, I need to transform the distributions to central moments first, and then you can calculate the cumulants. And for the streaming, I use an in-place streaming, so there's no explicit streaming. We just work with like changing some pointers to our variables. You can find both of these methods in Virtual Fluids, which is open source right now. And the papers are cited below. So let's come to the actual topic. It's using lattice-Boltzmann with the rotating object. And one approach is using just forces for the blades. But since I want to have the geometry, I have to keep in mind that the geometry moves over these nodes, and some nodes are inside the blade now. And when I move it, of course, they are not anymore. And you can do a simulation like this, but it's quite challenging to reinitialize nodes that were solid before and are fluid now. And also, it's from a computational perspective not so easy to have these nodes always changing. So I'm going with somehow more simple thing. I put the rotor on a grid which rotates. It rotates with the same speed as the rotor. And then I just have to take care of the coupling of this rotating grid with this static grid. So that's the main challenge of my work. Okay, so I brought for you a closer image of the grid coupling. Of course, it's in 2D to make it easier to see, even though the simulations are actually in 3D, but you can show the principle like this. And also it's quite small, just fit on the slide. So you can see the blue rotating grid and the green static one. And then we have these marked with this white dot, the grid on the edge, like the nodes on the edge of the grid, and also the same for the static. So these obviously they miss neighboring nodes. So they miss information for the collision in lattice faults. And we can get this information by doing an interpolation. So we can just use the neighboring nodes, 4 in this 2D case, or 3 then in 8, sorry, in 3D, like a cube around. And then do an interpolation to get the information to the other grid. So the interpolation gives us both the information at the edge, and also it couples the grids. So the fluid motion can travel. So to get to our interpolation, I have a few requirements. So it should be accurate enough and at the same time efficient. And to have like a nice parallel algorithm, it is beneficial to have just this small interpolation cell. But for the interpolation of the velocity, it's not sufficient to do like the obvious one would be linear interpolation. When you have 4 nodes, so a bilinear interpolation. But that would introduce a numerical viscosity, so we would have like a step in our pressure profile. So I need a quadratic interpolation, even though I have the compact cell. And then the other one is density, and we can use linear interpolation. Some people have tried quadratic for it as well, but I didn't do it yet. Okay, so I am using an existent interpolation as my basis. It's called compact quadratic interpolation, and it was developed for grid refinement. So when we have a finer grid around our objects of interest. And to start from the linear interpolation but get to quadratic, I will use like the shear stresses I can get from the cumulants. So since I have the distribution function, just to remind you to the start of the presentation, I can get from the second order cumulants the velocity gradients. I didn't bother to write the equation because they're like a lot, so you can find them in here. And then I can use these for quadratic interpolation, since they're like the derivatives of the velocity. Okay, so now I'm going to show to you the algorithm of this interpolation. And I'm going to start, of course, with the distribution at the source nodes for my interpolation, and then want to finish with them at the destination nodes. So first I can get from the distribution functions all these macroscopic quantities, then do the interpolation, bilinear for density and polynomial for velocity, and then take it all and reconstruct the distribution function. So what I told you so far is also valid for the grid refinement. Now what I added are these things for the rotating grid. The first thing is due to the rotation, we're not in an inertial system anymore, so we need to add centrifugal and Coriolis force. And if we want to change the rotation speed of the turbine, we would also need to consider Euler force. But I haven't done it yet. And then, of course, we need to transform between the frames of reference. Because this blue grid is rotated, we need to rotate our distributions somehow, and also at the tangential velocity. And I removed the slide. So during the rotation, I do not rotate the distributions themselves, the 27 ones, but I'm rotating the moments, so the velocities, and also the velocity gradients before reconstructing my distribution function. And also I need to add the tangential velocity due to the rotation, or subtract it depending on the direction, of course. So if I, from which I integrate. But since we're here at the parallel conference, I'm not going to talk so much about the mathematics of the interpolation, but also about the optimization for the computational performance. So I'm working with the GPU module of virtual fluids. So we run our simulations on GPUs. Yesterday, they talked about double and float. So we use float on GPUs mostly because then we can use the cheap consumer cards. But you can change a flag if you want to. And I mentioned before that I interpolated distributions. What I didn't talk about yet is that there's another step, because the grids move, the cells for the interpolation change. So this node may move to this cell. And in this image, I marked all the interpolation cells, like the source cells. So this is a source cell interpolating to this node. And you can see they're like quite scattered. So like this one could be an interpolation cell if you look at the circle, but it is not. And sometimes you even have multiple nodes in one cell, maybe like this one or this one, deciding what you want to put into what cell. So for me, I started with the update of the interpolation cells. And I mark for you to adjust the nodes moving around. And I want to get like the one node of the interpolation cell, then I know all the others when it moves around. And I want to do it in parallel and locally. And we don't store some relation from these, like where you can just use the coordinate and get back the node, because we usually don't need it and we are often limited in memory. But there's a way to get it, because for the collision, we need the neighbors of the nodes. We store them, but we don't store everyone. We store just the main directions. And then you can just kind of walk along the grid to get the new neighbor. So this one moves to here, so I can just go to this neighbor. And I know the direction of my rotation, so I don't have to check many neighbors. And see, get this coordinate and then check where my node moved. And if it moved far enough to be in a new cell. And for example, if I would rotate in the other direction and it would move to here, then I would have to go there and then there too. Because we only store the main directions to save memory again. And I call this logic, for those who are interested, I call it for these nodes, because I know exactly how many destination nodes I have, but I don't know if maybe the source cell is empty. So it's more efficient for me to call it for the destination node. The other part is the one I talked about, the interpolation. Of course, that should also be able to be run in parallel. And that is not hard, because the interpolation results only depend on this compact source cell. So the interpolation scheme is really helping there. And I read the source cell, write the destination cell, so there are no read-write race conditions. The sad part is there's still a little bug where I get like a 1% constant error, just depending on the angular velocity. So I didn't bring you any images of the results. I think that wouldn't be fair. But I brought you some performance results. So I ran it on a consumer card, as you can see. It's a gaming graphics card, and used 60 million nodes, so quite a medium-sized grid. And then I checked the performance for the uniform grid, then did the same number of nodes roughly with a refined grid. So you can see like how much performance does a refinement cost us. And then I added the rotation in. And you can see the rotation doesn't cost as much as the interpolation. So if I'm going to optimize, I think I'm going to start with the interpolation itself. And the expensive part, mostly of the interpolation, is the calculation of the cumulants. So this is my summary. I aim to do high-fidelity simulations of the flow around a wind turbine using the rotating overset grid with compact quadratic interpolation. And I parallelized it on multiple GPUs. I have to acknowledge my funding by the German Research Foundation. And also I want to encourage you to take a look at our repository. It's open source, and especially if you're interested in like the cumulant, you can look at the license and probably use it as well. Yeah, so thank you for your attention.
Thank you.